it's a tough class all the time, especially so when you got to do all the work your own. All right, so I'm going to go ahead and get on to the next topic, and then we could talk more on the break or just before the break when I stop the live stream if you have questions, all right? So I'm not sure if Trey is here yet. Oh, there he is. So Trey's here. So that's been working to have Trey do the questions in the chat. So feel free to dump any questions you want in the chat, and Trey will try to help with those chat questions. All right. So now we're up to one of our last big topics. This is a fundamental deal here. So I cannot stress enough that chapter 11 is important. It's also soul crushing, but after chapter 10, hopefully it won't be quite as bad. So let me start off with this one. Remember this equation that we used to have. Sum of force equals dp dt. Now, most of you probably say, oh, wait, isn't that just MA? Yes. So this is Newton's, what is it? Second law, Newton's second, okay? So there's Newton's second law, all right? This is the equivalent, whoops. That is the equivalent, right? Torque is the same thing as force in rotation land. So a force causes translation, a torque causes rotation. Now we're going to change the way we talk about momentum. This P here, I want to call linear momentum, okay? That is linear momentum. Or you could call it translational momentum. So this new concept that we're going to use over here, this L, is called angular momentum. So that's how we're going to use that. And one of the things I usually like to mention about this is many people, especially if you've had a chemistry class, already have talked about angular momentum in a way you may not have realized. Perhaps you've heard of quantum numbers and the way the periodic table is organized. All that stuff is physics, and the quantum numbers, the first number is an energy quantum number, n, and then the L number is angular momentum, and then m sub z is the z component of angular momentum. So if you're a chemistry person, you know what I'm talking about. It turns out this is very useful for understanding the the periodic table. All right, anyway, so here is our big definition, all right? And I want to be very clear here. Let me clear this out. We're going to use, to calculate angular momentum, most people want to know how to do that. We're going to use these two methods here. So let me move this out of the way. I want to stress this. If you have a point particle, and this could be an object that's moving around, like this point particle right here. It's a block traveling to the right. Most people don't think of that as having rotational momentum, but it has angular momentum. And I will make that clear to you in a minute. But for now, it's very crucial to know that a particle moving in a straight line has angular momentum. This is how you figure it out right here. Okay, so if you want to, notice R would be this distance from the pivot to the point. So notice it's got a direction. It's from the pivot. Just like we talked about in torque, you go from the pivot to the point particle. And now there's also this momentum term right here that's associated with, actually, let me do that one in a different color here. There's the momentum term, or MV, right? And that's this. And notice there's a cross product here, right? Cross products come up anytime you have this rotational element you want to get involved. So in this case, this describes, think about this thing. If you could, I don't know if you can, I'm going to try and stop the share for just a second. Imagine you have that point particle. My hand was going up. It's kind of hard to do, so let me just get my book out. Sorry for this. It's a hard one to do. All right, so I'm going to rotate the book to match my hand. So now, hopefully you can see right there. Okay, I'm lining up my fingers of my right hand in the direction of R, and then I curl my fingers to V, and notice my thumb points into the page. All right, so this is on page 83. I line my fingers up with R, curl them to V, and notice my thumb points into the page. It's this point particle, which is moving in a straight line this way, is in a sense rotating this way about this black dot. So again, so you can see that up close. There's the black dot here is the pivot. You go up, you line up your hands that way, curl them to V, and notice your thumb points into the page. That's the same thing as this point particle rotating around like that. All right, hopefully that helped a little bit. But if you've got your own paper there in front of you, that's the way that a point particle moving in a straight line can be thought of as rotating. Here's another way to think about it. Imagine if your head was sitting right there at that black dot and you wanted to watch this particle go by. You would have to turn your head to watch it travel, right? You'd have to twist your head and watch it go. So in that sense, that's the rotation, okay? So, all right. You could think of it as circular motion, where the motion speed and the motion radius is changing. So it's a circular motion where the circular radius is changing, right? First there's a long radius and then it gets shorter and it picks up speed anyways. So hopefully that gives you an idea that particles moving in a straight line really have this concept known as angular momentum. Think of it another way. If you're standing on an ice rink, all right, let's say you're standing there, somebody walks by and they hit you, or somebody throws a ball right at you, you're going to twist as well as go backwards, right? So if somebody throws a ball at me and I catch it, I'm going to start twisting, and there's a rotation associated with that. That's angular momentum, right? All right. So, yeah, I've got some actual examples of this in the problems in a minute. So, yeah, I will give some examples in a minute. All right. But I do want to get back to that screen so I'm not lost. We're going to do examples all day. So all day on this one. Now I want to point out something else here. This term R perpendicular. This is not the same as R perpendicular from torque. I want to be careful here. Look at this. This is a line that runs infinite direction. Okay, but this is not the line of action anymore. A line of action runs through a force. Again, a line of action runs through a force. This line is, I sometimes will call it the line of motion. So I don't know if other people do that, but that's what I do. So I'll call this the line of motion. That's different than the line of action, which even though they sound very similar. And so again, we have this right angle here, right angle. And this parameter right here is R perpendicular. We're going to call it the impact parameter. So the larger your impact parameter, it's almost identical to the lever arm in everything except name, okay? So if you have a big impact parameter, you have a lot of angular momentum. So notice right here, this crap right here, you might write this in. Notice that this is R perpendicular. So if you have your book and you're following along, you might add this as a possible definition. MV R perpendicular. That's another way to get L for point particle. Now, look carefully. This is a vector. So you also need to get the direction from the right-hand rule. For most of what we're doing, remember, things that are going clockwise would have into the page or negative k hat. Things that are going counterclockwise would generally be positive k hat. And just to make sure you can see that, I'm going to do it again. So remember, if something's coming out of the page, if it's rotating this way, we're going to tend to say the rotation axis is out of the page, so that's positive k hat. And if it's going into the page, that would be a negative k hat. All right, and remember, you got to use your right hand. So, yep, that's a great way to do it, Trey. Thank you. So there is actually an animation, I think, of exactly what Trey is talking about somewhere on my website, and I'll try and get the link later. Well, let's see if I can get it right now. Actually, let's not, because I want to keep the flow going. So yeah, that's a great, good job. The classic example as well is a baseball that you hear physicists talk about. The pitcher pitches a baseball, or a softball player or whatever. As they pitch it, think about your head having to watch the ball as it comes toward the plate. And then, of course, something interesting that happens, they've done the research on this, and evidently even the best human in the world cannot actually follow the ball once it gets within like 30 feet of the plate. So I guess professional athletes, softball players and baseball players, are estimating what they think the ball will do in the last 30 feet. And that's why you're able to trick them and stuff, I guess. I don't know. If you're into baseball, cool. I'm not really. It's, you know, I've watched paint dry already. I don't need to do that. But if you like baseball, good. All right. There's a lot of physics. There's a lot of physics in baseball. All right. Okay, so, all right. So we beat this up. We talked about a point particle, and we're going to use this impact parameter if we can. Now, for everything else, it's actually a lot easier. Well, I don't know. That's debatable. We could use this. Now, I want to point out, so I is just what we did all last chapter. Omega is what we did all last chapter. And so I guess it's worth pointing out there's rotational kinetic energy, which was 1/2 I omega squared. Okay, well, these two equations are similar, but they're not exactly the same, right? It's sort of like there was momentum, which was mv, and then there was translational kinetic energy, the 1/2 mv squared. It's the same old crap. If you remember, one of the issues we have with this problem, when you're doing an energy problem, you don't need to worry about the plus minus signs. When you're doing a momentum problem, you do need to worry about plus minus signs. Again, so when we did rotational energy problems, we don't need to worry about plus minus. When we're doing angular momentum, you will need to worry about clockwise or counterclockwise. Okay. Notice that this one will also work if you notice that mr squared, right? If we plug in mr squared right here, you could take one of those r's and an omega and make a v, right? So r omega equals v. So these are the same type of equations. And notice you get back this term here. It's a little bit hidden here because you got to assume this is actually r perpendicular. All right, that's a lot of crap there. All right. Let's scroll down a little bit. All right. So just like we used to have, I guess, how are we going to use these things here? So we could use torque and relate that to the change in momentum. That's a lot like the impulse equation, if you remember. Change in momentum over change in time is the sum of torque. Got it? If we have no external torque, this is where we're going to use this more often. Whoops. If this is true, if we have no net external torque, that's a lot of stuff in there. External net torque is 0. Then this goes to 0, and then we say angular momentum is conserved. Okay, so angular momentum is conserved if you have no external torque. Just like we said energy was conserved as long as there was no external work, or momentum is conserved as long as there was no external force, or if the external force was negligible. All right, so in practice, these are your two equations, right? Momentum 1 plus momentum 2 initial equals momentum 2 plus momentum 1 final. All right, and so this looks exactly the same as the momentum equations we used to do. Now, there is another one, the classic figure skater with their arms out and then they bring their arms in. That's a rotating object that changes shape. With those types of equations, we can say the initial moment of inertia times the initial rotation rate is the final moment of inertia, right? If you change shape, the moment of inertia changes. If you change shape, the moment of inertia changes. So good to know. All right. And then let's clear all this. And then this is just the introduction here to get us rolling. By the way, if you're going to code this stuff, we're going to talk about this in lab this week when we talk about the Euler-Kromer technique or the method. And so this is how you do that same technique. And so more on this garbage in lab this week, okay? More on this in lab. Let me read this last special note, okay? We could choose this for moving in a straight line, or we can use this for a point mass attack. Oh, this is a worse, yeah, so make sure you read this note really carefully after you maybe summarize and do a few problems. So let's get to a problem now, all right? And actually, I'll check the chat and see if there's anything. Okay. All right. Okay, so there we go. Let's see. All right, you guys are rocking. Okay, let's go do a problem, all right? Come on, there we go. So I'm gonna look at, let's start with 11.1. All right, so let's take a look at this one. You have a moon in a circular orbit about a planet. The moon has mass m, speed v, some crap. Okay, so let me make sure here. Okay, so this is the sun, or the wait, no, this is the planet. So that's the planet. And then over here, this guy is the moon. All right, and it's going with speed v, and it has mass m. Got it. Okay. And now here's the weird thing about angular momentum. Okay, this is something I want you to understand. It's an important deal. In every problem, you get to choose the black dot. In every angular momentum problem, you can choose the black dot. So in this problem, we could choose to say at point A, or we could choose it to be point B, and we could do angular momentum about either the green dot or the purple dot. And in fact, we could even do it about this point up here, or this point over here, or any point you want. The point of this problem that we're doing is to discover it helps to pick the best choice. So notice in part B, we will discuss which way seems more convenient to work with and why we should care. So just give me a little latitude, even if it seems crazy to do what I'm going to do here. Let's do this problem. For the instance shown, determine the angular momentum about the moon, angular momentum of the moon about point A. All right. And then we're going to do it about point B. All right. So I'm going to clear this out and go over to the solutions. So again, we're doing part A. Got it. Let me go over here. Whoops. All right. So hopefully this makes sense to you. Let's not overthink it. I'm getting the angular momentum about point A. All right. About point A. And make sure this makes sense here. So from point A, the displacement from A to the moon, it was 2r, twice the radius, to the right. The momentum of the moon was upwards. So in this case, j hat. All right. Don't overthink it. Stick it in there and you get this number. Got it? Similarly, when I do the point at the center, okay, if I go from B to the moon, I only go r in the I hat. And so notice I get this other number. The momentum is still the same. Notice what I just said. And notice this difference here. When I say momentum, I'm thinking P. When I say angular momentum, I mean L. So if you're noticing that today, all day long, if you hear me say momentum, momentum means P. Angular momentum means L. So watch out for that difference. A lot of times people will add the word linear, like I said, linear momentum. And that's probably a thing I should do, but I'm lazy. Okay. All right. Great. So notice the red one, you get 2, and this one, you get MVR. Okay, I'm going to stop that for a second. And then let's go back to the question. So now I want to look at the next part, all right? If the moon is at the top of the circle, and I'm assuming it's going to keep going at the same speed. It's orbiting in a circular motion. So I didn't really state that, but let's say it's going here, and it's still moving with the same speed v, all right? So now this is the momentum. P, it's still mv, but now it's going, I think, negative I hat, right? And notice in this case, if I go from here to here, that's my R vector. Or if you're trying to do the impact parameter, notice the impact parameter is now R. Agreed? Of course you agree, because you had no choice. I'm talking on Zoom. Anyways, all right. So we have the impact parameter here, or the R vector. Let's go look at the solution, and notice for part B is going to be the same radius as well. So what I want to do is go look at the solution again. All right, and so notice here's one way you could do it. So this was, I showed you how to do it with the impact parameter, but here's the R vector, R in the I hat plus R in the J hat. So now when you do this cross product, you got an I cross J, or an I plus J crossed with a negative I. So again, the I hat cross I hat term will equal 0. So then we get this, and notice we get this angular momentum. Whereas if you use point B, notice this. Notice, if I could, look at the red equation here versus here. They're not the same. Okay. What about the blue equation right here and right here? They are the same in both magnitude and direction. I'm just going to go out on a whim here and say, it looks a lot more convenient to use B. B seems vastly superior, way down here. Angular momentum is constant. No one in their right mind would ever pick A. This is a terrible point. That doesn't mean it's illegal. It's just not convenient. So remember this when you're doing angular momentum problems. If you get to choose the pivot point, let's scroll down there and see if there's anything else. More on this later. Oh, okay. Let's go do, it's easier to show it with a figure. Let me go back to the figure. Think about this. If I look at this point, there's the force due to gravity. Whereas if I look at this point, here's the force due to gravity. And if I look at another point, if the thing was over here, notice the force due to gravity is always directly towards point B. So how much torque does gravity exert about point B? None. And so by choosing this point, there's no external torque. If there's no external torque, remember, delta L over delta T is the sum of external torques, right? So if we choose the obvious pivot at the center in this problem, this goes to 0, and then we can say, oh, L initial equals L final. Vector. Vector. All right. I'm going to pause for a second and see if there's any questions about that. Is everybody good there? Looks like you are. It probably seems like I'm starting really slowly, but there's a reason for doing this. I just wanted to make that it's a huge deal that you can choose any point you want. So I don't know, at least to me, that's a big deal. All right. Why is physics so hard? I wish I knew. Yeah. Let's see. That is why the first is 2 times. Yes, exactly, Jay. And so if you try to choose any pivot point you want, I guarantee you can still do the problems, but you might not be able to use conservation of angular momentum. So that's so important. I'm putting it in the chat. Whoops. So again, if you choose to pivot wisely, we can do conservation of angular momentum. If you don't, it's not that your physics is invalid. It's not that you can't calculate angular momentum. It's that angular momentum isn't conserved, and then it's a really hard problem to do. All right, so let's move on. That was the only thing we needed to get out of that. Next, let's go to the next problem, all right? All right. So let's try and do this one here. 11.2, this is a page 84 still, I think. Still page 84, all right? Okay. Notice you're going to see this a lot now. Instead of calling rod's length L, you're going to see me try and do length D. I still probably have a couple of these. So I want you to start using D for obvious reasons, because L is now angular momentum. It's going to be confusing if we have 2 L's. So I want you to start trying to get in that habit, and I hope I've gotten all the typos out. If not, let me know. If I ever used L in this chapter, let me know, all right? All right. Okay, so we got rod. And so you could think of this as throw a ball at a stick. The stick is connected to the ceiling with a bearing. In class, we actually have a demo that does this, but we don't have it right now. Something maybe we'll work on in the summer or something, I don't know. But yeah, okay, so this mass right here is moving. Good. It's got mass m/2. Got that. It's distance d. Cool. Okay, so notice this blah, 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 blah. This is slightly important here. The motion of the clay can be considered a straight line motion. Obviously, you know that in practice it would go like this, right? It would start to fall down. But what we're told is it's moving so quickly that it's effectively straight line, all right? So yeah, ignore y motion of the ball. All right. Now, the clay impacts the rod at the end and sticks to it. What is, okay, and we're going to assume okay, so standard coordinates, gotcha. Normal x, y, z, good. All right. I'm going to give you one guess. What is the best choice of arbitrary point? So take a second, and obviously you don't need to respond. Just think to yourself, what's a good choice of pivot point? Here's a hint. In this problem, there is an actual pivot point. That's probably the one. So hopefully you thought about that. If there's a pivot point in a problem, why wouldn't you use that instead of, you could choose this point. There's nothing wrong with that. It's just impossible to do the work. So why? It's just, why waste your time? All right, got it. Hopefully that made sense. This is why you would choose that. Okay, now I need the impact parameter. Try and remember what that is. I'll give you a second to think. What is the impact parameter? All right. Hopefully you saw it. This, whoops. This distance is d. Notice that is perpendicular to the line of motion. So it's not line of action anymore. This is the line of motion. So the impact parameter is d. That's it. So how can I get the initial angular momentum of the clay? This is a point particle. Okay, point particle, if I was sitting here at this pivot point and trying to watch that point particle, if I tried to watch it go by, my head would have to rotate. So clearly, this is rotating about that pivot point in this direction. It's rotating like that. We don't think of it that way, but it mathematically is that way. Okay, so how do I get the angular momentum? M V R perpendicular. You could also say MV R and then sine of the angle, if you recall. So take a second to look on the previous page in your workbook, because if I keep going back, it'll be crazy. I guess I'll show you it really quick. This right here, right? This MVR, this, or you could say, whoops, where was it? Usually we say this for a point particle, MVR perpendicular. Okay, so going back. All right. Apologies for scrolling all over on you. In this case, I hope you agree. What's the mass we should use in this problem? m/2. The speed is v. And then the r perpendicular is d. Or if you were trying to do it this other way, you'd say, well, the distance is, oh my gosh. Ugh. You could say it's d squared plus x squared square root. And then you'd say, okay, well, let's see, I need this angle right here. Well, sine of phi is going to be, right, this is just making this clear. I just want to show you, you could do it either way. And you may be saying, why is he wasting my time? Well, I know what's coming next, so just give me a little latitude, will you? So in this case, sine of this would be d over square root of crap. And notice the square root would cross out, and you get the same result. So I just wanted to show you, you could get the same result if you use MVR sine phi, or if you replace this with this impact parameter r perpendicular, like the lever arm, but it's a little bit different. Okay, that's it. I'm going to pause for a second and see how you're doing, all right? Going to pause, all right? Hopefully that's making some sense. We're trying to build up to a real problem. So Jay, there was another example. Looks like Jay's watching the live stream instead, so that's cool. But yeah, all right, that's cool. Oops. Okay. Okay. Oh, did I miss your name somewhere? Oh, there's a bunny. Sorry, my bad. Jay, did that address your question about a practical example as well? If so, let me know. Okay, yeah. So what I did was I took a golf ball and I put some Velcro on it, and then I put a meter stick and I put a skateboard bearing in the meter stick so it could swing, and I just throw the golf ball at the meter stick and it hits it. And then before it's got linear momentum, and then when it hits and collides, they start to rotate, and you know it has angular momentum. And then what I'm trying to convince you of is that just because something has linear momentum doesn't mean it doesn't also have angular momentum. So that linear momentum is equivalent to some angular momentum with this r cross p. And so we could say angular momentum initial equals angular momentum final, and you can do that kind of stuff. All right, so that's, all right. Whoops. All right, let's go take a look at the next one. Unless there's other questions, or throw them in the chat if you got them. All right. All right, so pretty simple so far. Everything's been at right angles. Yeah, okay. Let's try the same type problem and go nuts with the whole deal. So this, if you could do this problem, this is exam level difficulty, maybe even a little bit harder. So let's see, this is stepping it up, all right? Okay, we've still got this, man, okay. Now we've got the same thing, but it's going at this angle. Okay, we're gonna assume it's straight line motion. It hits the center and sticks to the rod. Okay. After the collision, okay, gotcha. Okay. Oh, wait, notice this. This time the speed is unknown, but we're gonna call it the letter V. So just be aware, all right? And now hopefully it's obvious that in this case, you could choose any pivot in the world. Why wouldn't we choose the obvious one right here? There's our pivot. And so here's our line of motion. Well, actually, I'll let you do this one. Okay, so yeah, determine the impact parameter of the clay. And if you finish early, go through everything. And if, yeah, all right. Okay, so I'm gonna pause. Well, I guess I already started drawing this is the line of motion, right? So I'm gonna let you think to yourself or doodle on a piece of paper there. Think what you think the, imagine what you think the impact parameter is, and I'll check that chat question. Yeah. Well, what happened with this? Oh, yeah, I'll tell you after we finish this problem. It used to be just an impact parameter question, but then people would like, oh, well, how does it go from there? And then I just added in the rest, and then we're done with this chapter, right? Yeah. Yeah. Okay. Once you get the impact parameter, see if you could also get the initial angular momentum of the clay. All right. And answer in terms of the unknown. And this is a weird one where I actually let you answer in terms of the unknown. And then there's a couple of there's a review question there too. Okay, so if you're working at home on the impact parameter, I'm going to budge in here. We need a perpendicular line. We need the perpendicular bisector. So if you're not familiar with this term, perpendicular bisector, you've probably heard it in geometry. Remember that this line goes on for infinite distance in both directions. So when we draw a line that is perpendicular to it, that runs through the pivot, technically speaking, that bisects this infinite line of motion. So this is R perpendicular. I got to get that thing. So see if you can figure out how to get that. Fortunately, we know this, right? That line's not very thick. So this is D over 2. And now, wait a minute. We also know that is also D over 2. So I should be able to figure out this angle in here. I'll call this angle, how about I call this angle alpha, just so, well, that's a bad angle. How about I call it theta, okay? So if that's theta, take a look. Isn't this 90 minus? So this would be 90 minus. This would be 90 minus. So this would be theta. Okay. And I believe if I see this one, well, actually, this isn't the best way to go, but you could figure this out if you wanted to, right? Tangent theta is going to be d over 2 all over d. So I think from that you could figure out theta, but notice we really only need tangent theta, I think, if I'm not mistaken. No, we need cosine. So I'm going to do it this way. This side right here is the square root of d squared plus d over 2 quantity squared, right? And that's going to equal something. I think that's d over root 5 or something, or I don't know. That's going to be something. But notice I could actually get cosine of theta, right? I'm going to go to the solutions because this is killing me drawing all this crap, all right? That's a lot easier, isn't it? All right, whatever. But so if you do that, you can see all the numbers here. And I just want, this is what I wanted to emphasize right here. This is something that you might not be used to, people. Okay, look at this. R perpendicular is going to be d over 2 sine of 90 or cosine of phi, right? So right here, look at that triangle and verify you believe it. Verify you believe that you can get this from SOHCAHTOA on that triangle. All right. Now, this is something I want you to, this is a good thing, especially if you're a mechanical or a civil engineer. Rather than solving this problem for an angle and getting a number, a decimal number, try and solve for the function that you need. So instead of solving for phi, solve for cosine of phi. So down here in this trick, if I know this is phi, cosine is going to be d over that junk, right? Well, so that just gives me this number. And so then I can take this and plug that in up here, and I'm good to go. So hopefully this makes sense. That's a lot of stuff. I'm going to check with the chat here. I have no idea if you're getting this. Yeah, it's really useful in civil engineering. It's really useful in statics and dynamics. So that's worth typing something here. So we're going to use that trick all the time in chapter 12 as well. So you might be thinking, I'm not a civil engineer. Well, you do have to take chapter 12 of this course. So I recommend you get used to this trick. It's really convenient. All right. I mean, every single problem in chapter 12, we rarely need the angle if we do this trick. All right. So it is important that you get used to that. Okay. So if you had questions about that, let me know. Hopefully that figure is good enough. So I'm going to go back to the question and read the next part. Okay. Now I'm going to get part B here. Whoops. Let's do part B. Determine the initial angular momentum of the clay. All right. Well, that's not too bad. I know the initial angular momentum is mv r perpendicular. And I want to be a little bit careful now. In the last problem, I glossed over something. I meant to ask you, what did I screw up? And I forgot. Technically, angular momentum is a vector. So we need a direction, right? That's that stuff where I was standing up trying to use my right hand. So we also need the direction. I just want to stress that let's try and do the direction on this one, all right? The k hat or minus k hat. Okay, so in this case, I see it rotating out of the page, which I would say is positive k hat. So we're going to use this for the magnitude and then just slap on a k hat on there, right? That's supposed to be a k hat. Okay, so let's go look at the solution just so we don't beat ourselves up here. Okay, so this is m v are perpendicular. So maybe I could make this a little bigger just so I could annotate it. A little easier. This is the mass. This is V, and this is R perpendicular. Notice I didn't use R in this case. We already did all this work to get R perpendicular is this. So we got the impact parameter, let's use it. So you could clean this up in any number of ways, but this is good enough, okay? And then notice the direction is out of the page. So if I could, there's our K-hat, good job. All right, let's go read the next question. All right, so back here. And, you know, hopefully, I know I'm going a little slow, but I'd rather give you guys time to think and get your questions. So we could pick up the pace in a minute if we need to, all right? So apologies if it's too slow for you. All right, moment of inertia of the rod clay system after the collision, after. So notice it's gonna be rod moment of inertia plus clay moment of inertia. Let's go see it. Okay, so take a second, right? You got the moment of inertia of a rod. Think, is it 1/3, 1/12, or something else? Think to yourself. And then you got a point mass. How am I gonna stick that in there? Let's, oh, whoops, I hit the stop share button, wrong button. Sorry about that. So let's go look at the solution now. Total, let me make that bigger. Whoops, one more, there we go. So I know I want the total moment of inertia would be the rod's moment of inertia and the clay's moment of inertia. I looked this up in the table. Well, I notice it's 1/3 of the mass times its length squared. In this case, length is D, not L, because we're going to use L for moment of inertia. And then this is the mass of the point mass, and this is the distance, X, from the pivot point to the point mass. So when you do all that, you get this crazy fraction. On a test day, if you wanted to go decimal, I'm cool with that. I think I tend to use a lot of fractions in this chapter. Excuse me. I use a lot of fractions. I don't know why. That's just what I do. All right. Now we're going to use conservation of angular momentum. Now, technically, this is not angular momentum. What did I write? Think to yourself. This is not angular momentum. That is angular momentum, right? So I did not write conservation of angular momentum, but from a practical standpoint, we know everything's going to be in the K-hat both before and afterwards. So that's why I'm just going to say magnitude of angular momentum is conserved. In this case, because the K-hats always drop out. So just in case there was some lag, I'm going to say that one more time. All right, it's kind of a big result. Technically, we should be writing L initial vector equals L final vector. But if everything in a problem is rotating clockwise, or in this case, excuse me, counterclockwise, the K-hats drop out. So there's a K-hat here, a K-hat there, here a K-hat, there a K-hat, everywhere a K-hat, they drop out. All right, so clear all that. And then here's, this is not too crazy. So this is the initial angular momentum from MVR perpendicular. And remember, the M had an M/2. That's where that 2 came from. Now, the final state, it's easier to do the angular momentum with the continuous object pattern. So here I use the total moment of inertia. We got that somewhere. I know that. That's good. And then I can get the rotation rate. Cool. All right. So, and here, I don't think we know that rotation rate, but this equation is valid. So notice in this problem, V is an unknown and omega is an unknown. So V and omega are unknown, but we do have a relationship between them right here. Omega will relate to that velocity like this. All right, cool. And I'm going to stop for a second there or clear that out. If you have questions, definitely throw them in the chat there. So let's go back to the, whoops, questions. All right, so now, actually, I think we just did this one. Okay, so there's that. I got the rotation rate. So we've done this, 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 and this. What assumptions did I make? Ooh, this is good. You should actually take a second to think, okay? What assumption has to be valid if I'm going to use conservation of angular momentum? Under what circumstances can I say that? All right, so I guess I'm saying when and I'm going to throw the vector on here just to be clear, and then I'll check the chat and see how you're doing. Okay. Yep. You guys are on it. Okay, cool. So in this case, I want you to think, isn't there something exerting a torque on the rod? Think about it. This mass is going to hit the rod, and then it's going to start swinging. What force exerts a torque on a swinging object? Think to yourself, what type of force is it going to exert a torque when this thing swings? And I'll check the chat here. Not tension. And I'm going to try and draw this one. Yeah, gravity. So imagine, let me go this way, okay? Let me share a different screen, okay? Let's say we had this pivot point here, and we have a rod. So again, this is the pivot. Now, there's going to be a gravitational force acting at its center. If we think about that, oops, there's a vector this way, right? So this would be the R vector, and we would get a torque. So maybe oh no, maybe we shouldn't have done this. Oh no, should we not have used conservation of angular momentum? No. Well, are there other forces? Let's see. There's a reaction force that's holding it up. That causes no torque because it's at the pivot, right? The line of action for that force goes right through the pivot. So the reaction force does nothing. That's what it's called, the reaction force at the pivot. Usually that's just what we call it. Pivot force would be another name, but everybody calls it reaction force. All right. And then that's it, right? We're going to ignore drag. So why is it okay to ignore this torque? Why is it okay to ignore that torque? It is in certain circumstances, right? If the collision happens quickly, this should work. Let's see. So in this case, let me clear all these drawings. Imagine it takes just a split second here. Imagine if the clay has fully attached to the rod and it's only moved this far. There's still a tiny gravitational torque, but the torque due to mg is approximately 0. So if the collision happens quickly, which most collisions do, if the collision happens quickly, right? Oops, oh, something's going on funky here. I just wanted to stress, if a collision happens quickly, tension can cause a torque in some cases, and we'll see that in chapter 12. So tension is a force. Yeah. So no, tension is a force that could cause a torque, and we'll see that in chapter 12. I'm just catching up with chat here. If the rod was already swinging and the clay hit it, you could still use conservation of angular momentum, because during there, usually the forces in the collision are so much bigger than the gravitational torque. It's still, even though the torque would be non-zero, it'd still be approximately 0 compared to the torques involved in the collision. So generally speaking, as long as collision time is short, I'm adding it to the chat so you could read it. As long as collision time is short, we ignore that gravitational torque. And that would be true whether it's swinging down and not all the way or whatever. So yeah, that's a good question. I like to mention in momentum problems, we said the short collision time would allow us to ignore external forces. So now we could see this. This is a big deal. If you have negligible external work, use energy. If you have negligible external force, use momentum. If you have negligible external torque, you can use angular momentum. And that's the new thing. That's kind of cool. We're going to talk about that in depth later, but that's like pretty damn fundamental. Okay. Negligible work, use energy. Negligible force, external, use momentum. Negligible torque, external, use angular momentum. That's huge. All right. The whole last half of the chapter is just practice with that. So I'm going to save that for then. All right. Let's go back to this question. I'm getting lost. I forget what we're doing. Okay. So, in this case, this was part E. That's what we were answering. So you might be wondering, when can I use this new tool? Okay. If we want to use that new tool, let's go look and see if there's anything else I said here. There's what I said there, and see if there's anything in there that you have a question about really quick. Assume external torque is negligible. Doesn't necessarily have to be zero, but it should be negligible. External forces are gravity and reaction, assuming the collision takes place. Yeah, line of okay, blah, blah, blah. Okay, cool. All right, so now we're told this rod. Let's go back and get the question really quick. So we're asked, how much does the center of mass change? So to be clear, it says after the collision, it swings up to parallel to the ceiling. So after the collision, it looks about like this. And this is kind of convenient. If the ball is right here at the center, the ball will still be right here at the center. And notice the center of mass is going to go up just d over 2. This distance right here is how much the center of mass goes up, because the center of mass is right there. It goes up d over 2. That's cool. So now part G. Quick question, how do you do that one? What technique should you use for part G? Think to yourself. Hopefully this is automatic after the test. Speed makes you think probably use energy. Swinging rod, maybe, I shouldn't use kinematics because the torque is going to change, so I better use energy. Hopefully you thought that. Let's check. Or work, yeah, you could call it work, energy, whatever, same thing. Dane, I'm sorry. Dane, the thing that you care about, let me do that after this question, Dane. All right, I'll mention that, or look at page 93. Okay, so Dane, if you want to look at page 93. All right. All right. Sorry, I'm getting lost there. Where were we? Oh gosh. Oh, so we're doing an energy problem. Energy problem. All right. So let's go look at this one, and hopefully I did the energy problem. Use energy after the collision. It's a single object swinging, so I use my swinging energy equation. There's the work. We're going to assume that's 0. Initially, I set, so hopefully it's obvious, I set the initial height to 0. So if I could, just making that clear. Initially, we had this rod here, and afterwards we had this rod here. Whoops. Right, and we said, I'm going to set this height. That height is 0. So that means this height is d over 2. So that's why, in this case, the height initial right there is 0. Whoops. This height goes to 0 initially because I said this is height 0 and this height is d over 2. Hopefully that's clear. And now at the end, it stops swinging, right? If it reaches up to max height, so it's rotating here. So I have omega initial, We called that omega in the previous step. Omega final, it stops rotating at max height because it swings up and then it's going to swing back down. It swings up and swings back down. So now I get another equation. Aha! This is where it gets fun. I now have an equation for omega given. I could take that and shove it into here, and I could figure out V. So notice out of all that, oops, you could actually get the speed V, and a decimal would probably be a lot more instructive than this square root of 55 over 4 or whatever. But yeah, okay. Let's think what the point of this is. This seems like just a bunch of math until we think about the point. Let's go back and look at the question. Here's what's cool about this. You can shoot a bullet out of a gun into a block and figure out how fast the bullet is moving. This is how you could figure out the velocity of bullets coming out of a gun. And it works great. Now, obviously, I think you'll agree this problem would be a terrible way to do it, right? Why wouldn't you shoot this way, which is a lot easier to analyze? So this problem up here would have been a lot easier to analyze than this weird diagonal line. So yeah, but the point is we could do this one, and this has all the complexity pretty much that you need. Okay. And then basically that's a pretty good start to this chapter. Let me see here. All right. So, and then, regarding Dane's question, I just want to summarize. If you have a second, look at page 93. So page 93 has a nice chart. So everybody look at page 93 and I'll show it on the screen here. There. I think this is what Dane was talking about. This is pretty big deal, okay? So the big three, this is like, if you had to learn something out of this class, this is it, okay? So the idea is, if you want to use a conservation law, you make sure it's appropriate to use that. If you want to use this equation, make sure it's okay to use it before you do that. And if you could do that, that's a level up rather than just knowing how to do the math, right? You got to know when it's okay to use these laws, know when to use these laws. To that end, I want to point out questions 11.18. So in your book, the questions on pages 93 through 97. You don't need to do all those parts. You could just do part A. Okay. So that's the minimum that you should do for questions 93 through whatever. However, if you have time, you can do the extra parts. So that's supposed to be putting all of these things that we've been doing all semester together and identifying which equations it's okay to use. All right, so I'm going to stop the share and put that in the chat, and I'm going to end the live stream for a second. Okay, so